Imagine watching a high-speed electric train rushing past at incredible speed. It may be traveling at nearly 200 miles per hour, while pulling thousands of tons of cargo or passengers. The scale of power is enormous, yet all of it depends on a surprisingly delicate connection. At the top of the train, a single metal arm reaches upward to touch a thin overhead wire. This wire carries extremely high voltage, often around 25,000 volts. Despite strong winds, constant vibrations, and extreme speed, this connection remains stable. At first glance, this seems almost impossible. How can such a fragile system handle so much energy without breaking, losing contact, or overheating? The answer lies in a series of clever engineering solutions. Each component is carefully designed to handle stress, maintain contact, and ensure efficiency. This system may look simple, but it represents decades of innovation and problem-solving. The device mounted on top of the train is called a pantograph. It is responsible for collecting electricity from the overhead wire and delivering it to the train's motors. The name pantograph comes from an old mechanical drawing tool invented in the 17th century. That tool used a similar folding structure to copy and scale drawings. Engineers later adapted this design for use in trains. By the late 19th century, the pantograph became a reliable way to maintain contact with overhead wires. Its flexible jointed structure allowed it to move smoothly while keeping constant pressure on the wire. This design solved a major challenge in electric rail systems: how to maintain a stable electrical connection while the train is in motion. Over time, the pantograph design improved significantly. In 1955, a French engineer named Louis Favely developed a more advanced version known as the single-arm or Z-shaped pantograph. This design reduced air resistance and improved stability at high speeds. Unlike earlier models, it was lighter, more aerodynamic, and better suited for modern high-speed trains. The streamlined shape allowed trains to travel faster without losing contact with the wire. It also reduced wear on both the pantograph and the overhead system. Today, this design is widely used around the world and plays a crucial role in high-speed rail networks. The pantograph is not a rigid structure. It constantly adjusts itself to maintain contact with the overhead wire. Underneath the arm, pneumatic systems use air pressure to push the pantograph upward. This ensures consistent contact regardless of changes in height or track conditions. As the train moves, the overhead wire may rise or dip due to bridges, terrain, or construction. The pantograph responds instantly, adjusting its position to follow these changes smoothly. This dynamic movement allows the system to absorb shocks and vibrations, ensuring uninterrupted power supply. One of the biggest challenges in this system is friction. At high speeds, the contact point between the pantograph and the wire experiences intense stress. If both surfaces were made of the same material, the friction could generate enough heat to cause serious damage. Over time, this would wear down the components and potentially lead to failure. To solve this problem, engineers needed a material that could handle both electrical conductivity and mechanical wear. Instead of using metal, engineers chose carbon graphite for the contact surface. This material is similar to what is found in a pencil. Carbon graphite is an excellent conductor of electricity. At the same time, it acts as a natural lubricant, reducing friction between surfaces. As the pantograph moves along the wire, the graphite slowly wears down. However, this is intentional. The carbon strip acts as a sacrificial component, protecting the more expensive overhead wire. When the strip becomes too worn, it can be easily replaced, making maintenance simple and cost-effective. Even with graphite, there is another potential problem. If the contact point remained in the same position, the constant friction could create a deep groove in the strip. Over time, this could weaken the pantograph and lead to failure. Engineers needed a way to distribute the wear evenly across the surface. This challenge required a creative solution that went beyond simply choosing the right material. The solution was surprisingly simple. Instead of keeping the overhead wire perfectly straight, engineers designed it in a slight zigzag pattern. As the train moves forward, the pantograph shifts slightly from side to side. This causes the contact point to move across the width of the carbon strip. This movement spreads the wear evenly, preventing grooves from forming in one spot. In the railway industry, this design is known as a stagger. The entire system works together as a balanced solution. The flexible pantograph maintains contact, the graphite strip reduces friction, and the zigzag wire ensures the specific problem. And together they create a reliable and efficient system. This combination allows trains to operate at high speeds without damaging infrastructure or losing power. What appears to be a simple metal arm is actually a sophisticated piece of engineering. It adapts to movement, manages friction, and maintains a critical connection under extreme conditions. The next time you see a train passing by, take a moment to look at the pantograph. It represents a quiet but essential innovation that keeps modern rail systems running smoothly. Understanding these hidden details reveals how thoughtful engineering shapes everyday life in ways we often overlook.